Good afternoon, everybody. Mark Astonga here again, and today we're going to cover our first lab session for the Metrum Institute 210 course. I'll be monitoring questions as we go along here. So if you have any technical difficulties, post a question there, or if you have questions about content, please also post those on the question tab. So I thought that the first thing I would do in starting our session today was to review some of the questions that came to me after the last lecture topic. So you see here on our discussion site, we've got a few threads. I'm going to pull up one here that we had a couple of posts on. This is the weighted least squares questions. And a couple of questions came up. One of them was about specifying a weighting based on prediction. And the exact question was, what if we fixed the weight in weighted least squares to 1 over predicted instead of 1 over concentration or 1 over concentration squared and so on. And so, yeah, that's a perfectly reasonable thing to do. It's got a special name. It's known as iteratively reweighted least squares. And it's iteratively reweighted because at each iteration of the parameter search, the denominator in that objective function changes because the prediction changes. Whereas if you're using a weighted least squares based on concentration, at any one time point, the weighting is always the same. So in iteratively reweighted least squares, the denominator of the objective function does change as the prediction. So that's something that we could do, and in fact, we'll try to implement that today in the lab session using the spreadsheet versions of these various least squares objective functions. Then another question was raised about how to simulate, somebody was exploring how to simulate residual error in an exponential form. So we talked about constant variance models or additive residual errors, and we also talked about heteroscedastic variability, and the one case that I mentioned was a proportional variability. Well, of course, that's not the only possible pattern for the variability, and another one we might consider is one where the variability varies exponentially with the model prediction or with the observed data. So to simulate in Excel, and this is not, I'm not trying to teach you how to simulate in Excel as part of this course, but it does illustrate how an exponential error is coded. If we wanted to derive some dependent variable here, y, which is our data point, through simulation, well, y would simply be equal to the prediction, and this prediction would arise from whatever algebraic or differential equation model we have for the prediction of a concentration point at a particular time, times some exponential random error. And what you see here is that there's simply stated that we have an exponentiated random number generator, or pseudo-random number generator, which is generating a normal random variate with a mean and a standard deviation. And I illustrated below here that if you wanted to simulate an exponential error that's about a 30% coefficient of variation, then the variance would be 0.09. Square root of that is the standard deviation, and that would be equal to 0.3. So since Excel uses standard deviations in its normal distribution parameterization, you'd write that like this. You'd have y equals the prediction times the exponentiated pseudo-random number here, which is from a normal distribution, mean 0, and standard deviation equal to 0.3. Okay. So those were the couple of questions that came across. I think there was also another one that didn't make it to the forum here, but I got through email about weighted residuals, and we'll try to address that as we look at the sample spreadsheet. Some of you also noted that you had difficulties with the data set, opening the data set, and I did respond to that in the forum. I hope that all of you were able to open that. It wasn't really a requirement for preparation for today, but the problem that we were having there is that there's a bug in Excel, and if you try to open a text file that's comma delimited, and just so happens to begin with the characters ID, Excel won't be able to open it. It's just a bug. There's nothing wrong with the file. It's a text file. But what I did is as I reposted that file in case you wanted to open it directly in Excel, I changed the initial characters to SID or subject ID so that Excel wouldn't have that faulty appearance of the bug. This is an old bug in Excel that I know that is something I recognized probably about 15 years ago when we reported it to Microsoft, and they still have not fixed it. I don't think they intend to fix it. But anyway, that file is just a text file that could be read easily through any text editor. You could pull it into R or S Plus or SAS, whatever tool you'd like. But Excel happens to have a problem with it. Okay, so the new file there doesn't have that problem, and that's what you can use moving forward. Let me open up the spreadsheet that I asked you to look at, and we'll walk through this. So before I move on to that, let me pause and look for any questions here. Okay, looks all quiet. I'll walk you through the spreadsheet, and we'll discuss the different objective functions and how they're calculated. So what we've got here is a tool that's useful for teaching purposes, and it's set up where the first tab is a simulation, and this just allows us to create a simulated data set that we will try to analyze on subsequent pages. And then after that, you'll see there's a linear regression method, there's an ordinary least squares, weighted least squares, and extended least squares. So we'll walk through each of those. So let's take a look at the simulation first. You'll see at the top of this page and every subsequent page that I have some of the parameters necessary for the simulation. We're simulating an IV bolus concentration time profile. The dose here is 1,000 arbitrary units. It could be milligrams. The volume is 20, maybe liters, and the clearance is 3 liters per hour, let's say. There's also a residual error with a value of 0.04. In fact, this, I think my notation here is not quite accurate because I think we use this as a standard deviation. One way to do that here is we'll look at the formula bar. View formula bar. There. Right. So when we do the simulation, you see I'm using this value with G6. Yeah. Okay, so I am this is the variance because I do take the standard deviation of that in the denominator. In any case, the way we set this up here is we have time data and we have concentration data. Now this concentration column simply represents the prediction under the model parameters where the volume distribution is 20 and the clearance is 3. And if you wanted to change the way that looks, you could change clearance and you'd have a different prediction there. But let's go back to the value we had used originally. In the next couple columns, and this is just for your information, it's not necessary to understand the concepts, but we're adding some random noise to the data. And in column E, we're doing that using a proportional residual variability, and in column F, we're using an additive residual variability. You'll see that E is proportional because it pulls in a measure of the concentration here. So we're using D6, which is the prediction at this time point. times the square root of the variance. Okay, so that allows us to inflate the variability at the higher end of the prediction range and where the variability will be smaller at the low end. So this is a proportional residual variability. That's how we're simulating the data. So this is just to set up the data set. And what I've done here is, recalculated this a few times. And I pasted one of the outcomes down below here in row 26 through 44, column C, just to have I just pasted values there so it would be a fixed representation of the data so that we can use the same data set across all subsequent comparisons. Okay. So the next plot here, the next page, is a linear regression analysis of this nonlinear data set. So remember when I presented this in the lecture on Tuesday, we discussed that linear regression can be useful when the variability, or when the relationship between the predictor and the dependent variable appears to be nonlinear, but the transformation could result in a linear relationship. So that's what happens here when we take concentration time data from an exponential decay and we log transform the concentration data. We end up with a linear relationship. And you see that in the two plots here. The top panel represents the observed data on the linear scale, and then the bottom panel represents the same data set, but now under a transformed concentration data, log transformed. So it's a semi-log representation. So one thing we see is that the structure of the relationship changes from something that's nonlinear to a straight line. And we also see a change in the shape of the variability. So up in the top panel, we notice that the error, or the noise around this prediction model, you see the data points scattered quite a bit more broadly at the high end than at the low end. That would be consistent with a heteroscedastic variance. In this case, we would probably assume that it's proportional or exponential, something that's increasing with the observed or predicted concentration. When we do the transformation on the log scale, two things happen, right? We transform the relationship to a linear relationship, and then we also see that the variability in the data, that pattern changes. And we go from something that was clearly proportional to something that's nice and evenly constant, or an additive relationship. This is what we call a homoscedastic residual error, or a constant residual error. And in this case, the log transformation is doing a good thing for us, because we want to perform the regression on a scale where the data points in the regression are accounted for in a constant variance term. And so, as we mentioned in the class last week, weighted least squares is one way to do that. Maximum likelihood approaches with an estimated residual variance is another way to do that. But here we're showing that the transformation itself helps us. And so that's a useful thing in this case. So what we're doing in this particular model is that we're applying, we're going to estimate the maximum likelihood estimates of volume and clearance. So row 3 up here represents the parameters to be estimated. Row 4 is the true values that we pulled from the simulation page. In row 3, you see that we've arrived at some estimates here. 23.3 liters and 3.26 liters per hour. These were derived by doing that closed form solution. Remember, we said that to determine the maximum likelihood estimates, one of the things you could do is to solve that first derivative equation for the point when the first derivative approaches 0. That's the derivative of the model parameter with respect to the objective function, or with respect to the likelihood. Well, that's what we're doing here in linear regression, and since it's a straight line, that's a closed form solution. We don't have to do any computer-based numerical iterative technique in this very simple model. And you'll see that we parameterize the model in terms of a slope and intercept. M is the slope, B is the intercept, the y-intercept. And what I've done here is that these track back to calculations below, which are just the simple linear regression function in Excel, or I'm using OpenOffice here, but it's the same idea. You see that we estimated the parameters of this linear regression, where the intercept was 3.76, the slope was negative 0.14. We can even estimate standard errors for that, and then a p-value for the slope. Well, that's a closed form calculation, and so you can use the standard function built into the spreadsheet tool to do that. Then you just simply back calculate those here, where volume is going to be your A3, which is your dose divided by your concentration at time 0. So E7, here's your prediction at time 0. Clearance then is going to be negative B3, right, which is volume, times F3, which is the slope. Okay, and the rest of the work here is just performing the log transformation so that we can plot the data and run the linear regression. So the regression is done on not the first two columns here. The regression is done on time and log observation. Okay, so that's a linear case. Straightforward. It's not going to happen many times in your life that you're going to only have to analyze an IV bolus dose, single dose, where a linear regression transformation actually solves the problem. And this one here actually works quite well because we do go from that proportional variability to an additive type relationship, or a constant variance model, which does support our regression estimate. If you remember in the notes, I had an example that was sort of the opposite. It went from a constant variance in the concentration time profile, but the transformation changed that, and it ended up in an inflated variance at the low end, and that's a bad thing. If the variability pattern at the level of the analysis, or the data that you want to analyze, becomes non-normal or non-constant, excuse me, then you've got to do something with respect to weighting to adjust for that. So in our case here, the linear transformation does the weighting for us. So then I plotted out a couple diagnostic plots. Here's the predicted versus the observed, and you see scattering around the line of identity here. That's the dark line. It's that if we had a perfect prediction, all points would land on that line. And you see the proportional nature of the data. This is plotted back on the linear scale. The data are more tightly clustered at the low end and more variable at the high end. Residuals versus prediction. Here's a nice example of a proportional relationship where you see as you increase the value, the spread in the data becomes broader. Again, these are pretty well centered around 0, but you see that pattern, that sort of sideways cone shape, which is indicative of a proportional residual variability in the data. Remember that the residuals versus pred plot tells you about goodness of fit and also the pattern of the variability in the data set. And then if we plot it versus time, we see sort of the opposite effect, and that's because this is an IV bolus, so the highest concentrations come first in time. Now there's no weighted residuals plot here because we didn't actually weight the data. It was just a linear regression transformation, but we see that back in that original plot that the transformation does result in a residuals pattern that is quite even across the prediction range. Okay, so that's the easy case. That's linear regression. Now we're going to stick with this IV bolus model, but now we're going to pretend that we can't do linear regression, and we're going to have to use an iterative search-based algorithm based on one of the least squares objective functions. So here's the first one. ordinary least squares. So does everybody remember what that objective function looks like? Well, let's take a look. If we go here to the objective function for the first point, you see that this is related to the observed, B7, minus the predicted, C7, squared. Okay, there's no weighting involved here. There's no, the denominator is 1, so there's no adjustment for heteroscedastic variability. This is a very simple objective function, and you know, it sort of makes sense, but it does not acknowledge the residual variability pattern that might be heteroscedastic. The setup is the same, where we have the true value parameters here, 20 and 30, and the estimated parameters are here, 21 and 3.13. The prediction here is based on your simple IV bolus prediction model, so it's dose divided by volume times e to the minus clearance divided by volume times time. So that's an IV bolus expression. We calculate a prediction for every data point, and the only thing that's different here is time changes. So we have A7, A8, A9, A10, and so on. So there's a prediction for each data point. There's also a contribution to the objective function for each data point. So remember when we were talking about maximum likelihood, we first talked about the likelihood for a single data point. Well, that's this piece, or at least it's an approximation of that using an ordinary least squares objective function. But there's an objective function contribution for each data point. So here's the contribution for the first data point, the second one, the third, the fourth, fifth, and so on. So each data point has a contribution to the objective function. Now, if we want to optimize the estimates of these parameters, we can't do this in isolation data point by data point, so we have to summarize all of them. And since we're working with something that's approximately a -2 log likelihood, so we're on the log scale, how do we summarize up all of those objective function values? We take the sum, and so that's what this does here, is the sum of all of these individual contributions to the objective function, D7 to D25. Okay? So if we sum up all of those data points, now that's our overall objective function for the entire data set. And I just have it repeated here just so it's at the top of the page, but it's the same value. Okay. We calculate, in this case here, a weighted residual, but really there is no weighting going on in ordinary least squares, so you see the weighted residual is equal to the residual, in that it's just the observed minus the predicted. There is no weighting in ordinary least squares. So let's solve this problem, and let's go back to how we originally described a regression, a nonlinear regression problem, and that's where we have an observation data, concentration time data in the right panel here. We propose some structural model. Well, we think that might be an exponential decay, so we've proposed an IV bolus exponential decay. And then we estimate some parameters for that model. Well, what you see here in this sheet are actually the optimized parameter estimates. If we were just looking at this, we might not be so close. So I'm going to change these values. Let's say our best guess was from, maybe it's from some non-clinical extrapolation to a first-in-human study, or maybe it's from a prior study, and our estimate of volume and distribution there was about 30 liters. Okay. Then we also can adjust our estimate of clearance here to something that might be more realistic. The 3.13 is an optimized estimate. What we might have seen is actually a prior estimate. Maybe let's say that estimate was about 4.5 liters per hour. Okay. And you see here in the right panel that by plugging in those values, the pink line here is the prediction line. You know, and if we were a little further off, let's say our clearance was even higher, let's say it was 6.5. You see that our estimate is reflected here in a prediction that doesn't quite coincide with the data. but it's in the general region. This let me actually refresh this for a minute. It looks like the graphics got a little fuzzy. There we go. This particular type of exercise, where we propose a model structure, we plot out the data, and we plot out the model prediction at our initial estimates for the parameters. This is a very useful thing to do in any modeling problem. The estimates here are representing our best guess, and we get an idea of how good our best guess is by taking those initial estimates and plugging them into the equation or the prediction model and comparing them to the observed data. So let's say we had started off with something really off the wall, like 40 for volume and 9 liters per hour for clearance. Now we'd see very clearly that our initial estimates aren't even putting us within the range of the data. So this is a quick check on the validity of your initial estimates, and right away tells you that you should probably revise those. You might go back and look at the literature. You might play around with another value and see if you can get somewhat closer. And so maybe we got this closer, like 5. And you see, okay, that's better. Maybe that's good enough. Okay, so that's our starting point. You see we have an objective function value here of 1532, and there's a little chart that shows you what that is. How do we get that objective function to help us to optimize the parameters? Well, it's a -2 log likelihood. What we want to do is to minimize that objective function. So in Excel on the Windows side, and in OpenOffice, which I'm using on a Mac here, there's a solver tool that would allow us to address this. And the solver is kind of neat. This implements some of those iterative search methods that we talked about before. It has some options, and you can choose which algorithm you'd like. We don't want the linear solver. We want one of these other algorithms. The setup is slightly different in Excel, but it's the same idea. Okay, so what we want to do here is we want to our target cell. Well, our target cell is actually the objective function value. Okay, E7. And what we want to do to that is we want to set it to a minimum. We want to minimize the objective function by changing cells. Well, what are we going to be changing? We're going to change our parameter estimates. Cells B3 and C3. Okay. We can also set constraints in those parameters. So, for example, we might want to say the parameter estimates here, volume and clearance, have got to be greater than 0, so or greater than or equal to a very small number. But we don't want a negative clearance and we don't want negative volume, so we want to constrain the space to prevent that. Okay, so those would be some of the typical settings we would define, this is typical of any regression program. Now I've got a couple of requests here to show this again, so I'm going to do it again. Bear with me for a minute. Let me close up and then we'll reset the solver piece. Again, this is an add-in in Excel. If you don't have all of the functions included in Excel, you might not see this, but you can, if you choose Tools, Tools, Solver. Now in Excel it might be in a slightly different place. I'm using OpenOffice, but I think it is still under the Tools menu. And if it's not there in Excel, you can go Tools, and then I think this says Add-ins, and you can install the Solver add-in. But essentially, the solver is just an iterative search tool, again, where we're taking the target cell, which is the objective function value. We're going to minimize that by changing cells here, our estimates of the parameters, B3 and C3, which is the volume and clearance. And we're going to do that under the constraint that we want those cells to be greater than or equal to some small value. We want them to stay positive. Okay. Okay. In order to run this, then we can allow it to iterate and find a solution. So we click the solve here, and so it's going in progress. And you see as it's proceeding, you see the predictions are changing as the different parameters are explored. And it's trying to hone in on something. It looks like it's gotten pretty close now. And it stopped. Okay, and you see in this particular solver, it tells us that there were 60 iterations out of 2,000, and it stopped due to stagnation. Stagnation in this case, and it's going to have slightly different language in Excel, but I'll explain what the concept is anyway. Stagnation means that the parameters aren't changing anymore, and that's usually one of the criteria used in a maximum likelihood based objective function search, is that if the parameters don't change from iteration to iteration in more than, let's say, 3 significant digits, the problem is assumed to have converged. And you can set that at different values. You know, you could ask for more precision or less. But in most cases, the default is 3 significant digits. So this is just saying that both volume and clearance now, as the search continues, aren't changing past the 3rd significant digit. Okay, so we can keep that solution, keep that result, and you see now our objective function is down to 440. It was 1600 before, and we also see that the parameter estimates have moved from, I think we had 40 and 5. They've moved closer to the true values, and then the goodness of fit seems to have improved as well. So this iterative search algorithm seemed to do a pretty good job for us. We've minimized the objective function. We've got some parameter estimates. Now in the real world, you're not going to know what the true values are. In the real world, you're not going to know what the true values are, and so what you're going to end up doing is relying on other diagnostics to make sure that you've reached a global minimum. So one of the things we talked about doing was to try from different initial estimates. So we could do that here. Let's change our initial estimate for volume and distribution to, instead of 20 liters, let's change it to 12. So we'll go on the lower end this time. And then for clearance, we'll also go on the low end here. Let's choose 1 liter per hour. So now we're starting at a completely different part of the parameter surface. In fact, we're quite far away from the true data when it comes to our prediction. But we'll give it a shot, see what happens. The setup is exactly the same here. We're iterating on the same values of the parameters. We're just starting with different initial estimates. So we'll solve now. And you see this solver does a pretty good job of quickly honing in on realistic parameters, it looks like, at least from the prediction. And now it's just iterating to see how stable those parameters are, and now it's stopped and found a solution. And look, lo and behold, it comes up with an objective function of 442, which is the same value we had before, and the same parameter estimates. You could do this again to be sure, but we've done it now from 2 very different sets of initial estimates, and we ended up at the same place. So to me, that's good. Provides good confidence that we're at a global minimum with respect to these parameters. Okay. Next, we're going to look at diagnostic plots, because remember we said that another check of the model is diagnostics. And I'll try to illustrate a case in a few minutes here of when we hit a local minimum, but let's see what happens. So let's go to the next tab, which is OLS pred versus DV. So there's the predicted versus the observed values. Again, a pretty decent scattering, random scattering around the identity line. That's what we want to see. Residuals versus prediction shows you that sideways cone shape. which is immediately indicative of a heteroscedastic residual variability pattern in the data. Doesn't tell us anything about how our model weights it, but it tells us that that's the pattern in the data. And then we see a similar pattern for time, higher variability at the early time points where the peaks are. Now there's no weighted residuals here because ordinary least squares doesn't have a weighting factor. It's just a factor of 1. Well, let's try one more time back on ordinary least squares, and I'm going to try to get this thing to fall into a local minimum. I don't know, it's a pretty well-defined problem. We've got lots of data. It might be difficult to do, but let's see what we can do here. So let's get this off the mark. Let's put the volume at 90 and the clearance of, let's make this a little more shallow. Okay, let's see what happens here. Now that's not a very good starting point. You see from the prediction we've almost got a straight horizontal line. Those are different initial estimates. Let's see what the solver will do here. Same parameters again. We're going to iterate now and see if we can find a solution. It might take a little while too. So okay, great, we did it. So now take a look at this. We'll keep this solution. We ended up with a volume estimate of 64 liters and a clearance estimate of 0.2 liters per hour. But look at the prediction in the data. They're very discordant here. It's not at all like the relationship we had before. Look at the objective function as well. Our minimum is at 440, and now this objective function is 2,615. So this is an illustration of a local minimum. The minimization criteria were sufficient to stop the search, but we're clearly not at the best prediction here. So you can see it right now just by the high objective function compared to what the objective function was before. But if you look at this plot and the other diagnostics, look for example at the pred versus observed, it's not a very good relationship there between the two. Residuals versus prediction, this is very telling. You see a large run of negative residuals crossing over to some positive residuals. And again, residuals is the observed minus the predicted value. So when you see a negative value, that's an overprediction. A positive value is an underprediction. And then a similar problem versus time. So these diagnostics show us quite clearly that the solution is not optimal. Now it could be that the model structure is wrong, or it could be that our parameter estimates are wrong. And we know that it's the latter because we've already found some parameter estimates that seem to solve this pretty well. And we'll just do one last run here that's got some more reasonable initial estimates. And one way we could have known this from the start is that just by making this plot of the prediction at the initial estimates on top of the observed data, you can tell right away that whether you're in the ballpark or not, that last set of initial estimates wasn't even close to the shape or the magnitude of the prediction model. So now if we get something a little more reasonable, we're going to run the solver one more time. And we should end up with something that was pretty close to the 440 objective function that we've been getting with decent initial estimates. And yeah, that looks like where it's headed here. It's just rounding up. Here we go. Say OK, keep the result. And we're back at where we were before, same parameter estimates, same objective function value. So you see there, we ran the same model 4 times, each with different initial estimates. 3 of those initial estimates were reasonable and within what we would think to be a reasonable range based on prior knowledge, but they were all different. They all ended up at exactly the same place with respect to the objective function and the parameter estimates. It was just that 4th one that was that landed up in a local minimum. But if you run this if you keep this principle in play where you start that model and rerun it from different sets of initial estimates, you're going to be able to diagnose local minima pretty well. In addition to that, look at the diagnostic plots, and then just look at the relationship of the predicted and observed at the initial estimates, and that can also be helpful. So even though this is just a simple Excel spreadsheet, it still illustrates those basic concepts that we'll use with much more complex nonlinear regression modeling tools. Okay. Any questions on ordinary least squares before we move to the next topic? Okay. Weighted least squares next. Now, we're going to do the same sort of thing here, and right off the start, I'm going to give ourselves a guess. We'll start again at 15 and, let's say 15 and 2 liters per hour, so that we're kind of close, and we'll use similar initial estimates. Now, this is weighted least squares, and the objective function is going to change, of course. Now, let's take a look at what that objective function looks like. You can see here that it's the observed minus the predicted squared, just like OLS, but now we're dividing by B7. B7 is the observed value. So our weighting here is 1 over concentration. 1 over concentration here, or 1 over OBS, is multiplied by that sum of squared differences. You can see we have an objective function contribution for each data point. Each one of these is weighted by the observed value at that point. Here you see versus B13 divided by B14, B15, and so on. Again, to summarize all of these, we sum up all of the individual objective function contributions to give us the overall objective function contribution. And then we can calculate a weighted residual and a residual. So the residual here is simply the observed minus the predicted value, same as always. But the weighted residual now is that residual weighted divided by whatever your weighting function is. And here our weighting function is just the observed value. Actually, I've got it weighted by the predicted value here. We should change that. That's a typo. This should be weighted by the observed value, which is B7. Okay, that's my error. That'll also work, and it's more in line with the iteratively reweighted least squares, but we're doing weighted least squares, so we want to weight the weighted residual. We want to weight the residual by the observed value to derive a weighted residual. Okay, so now we can do the same sort of thing. We'll run the solver again. Tools, solver, same things. We're going to estimate by changing cells B3 and C3, so it's the same setup as we had before, and we're going to minimize that objective function. So here comes the solver.